problems faced by software engineers typically are of two types: systemic problems and technical problems. And the problems that are associated with technology are typically easier to solve. I'm not suggesting that there are no technological problems faced by software professionals. What I'm saying is that systemic problems are difficult to, first of all, understand, and secondly, it requires change on part of behavior of software professionals. And cultural changes have also to be introduced in organizations. Typically, software process issues which are critical are of four types. Number one, they are quality related issues. People make mistakes, processes are not well defined, and standards are not followed. And people are simply not aware of the importance of technology, the importance of quality in software engineering. Now, why is that the case, that people are not aware of quality issues? It is because that programmers are very techy people, and they want to hack their way into completion of the project and work on other projects. But that, we know, is not the right approach. It behooves an individual as well as an organization, let alone the entire software industry, that investments should be made into quality awareness programs. So that's one area where we need to focus as far as software processes are concerned. The other area is product technology. The technology is changing rapidly. The languages are changing, the platforms are changing, both the hardware and also the supporting software, the interactive development environments, configuration management tools, and so on are changing rapidly. New things are being added, new languages are being added very frequently. And so there is always a challenge to keep up with the product technology and to ensure that a new product interoperates with other previously existing software products. And so this is a challenge that every project manager has to face whenever a project is launched, vis-a-vis that if the requirement is such that this new product will be interoperating with existing products, how would that happen? And what are different technological issues that must be addressed and resolved in some cases? Then is the most important and ever-present requirement instability problem. Many times requirements are not known, they are unstable, and they are misunderstood. And this problem persists from day one of the software industry. And it will probably continue to be with us because of the nature of the requirements and because of the nature of humans and how humans communicate using natural languages. And so natural languages by their design are ambiguous, and so the inherent ambiguity in stating the requirements is always there. And obviously, whenever a new idea is created, all of its associated things are not fully understood. And so as time goes by, we continue to learn about the dependencies and relationship that exists within a problem space and naturally within the solution space. And finally, one of the more important points or issues that need to be addressed as far as software process is concerned is complexity. The economies in the new world are increasingly dependent on complex software solutions, and software solutions are becoming more complex by the introduction of the previous 3 points that I've talked about. So first of all, the application domains are becoming complex, and on top of it, we have other issues like quality, awareness or lack thereof, and issues related to product technology, and most importantly, requirements and stability are contributing further in adding the or increasing the complexity of software product as well as process. So those organizations, and I must say all of them, all the organizations who are in the software industry, face these issues of quality, of product technology, of requirements, instability, and complexity. They need to find ways to address them. And one way they can do so is by the introduction of what is known as process architecture. The process architecture allows or permits these organizations to represent and manipulate the process at the U level, and then selectively to refine those processes at W and A levels. We have already had a discussion on what U level processes are and what W level and A or atomic level processes are. In other words, we can say that the universal, worldly, and atomic levels of software process models can be presented in the process framework, and that is a huge advantage as far as the process definition is concerned. So we can say that a process framework will be able to establish and define policies, procedures, and standards. Now, if we can do that, we can refine the policies into procedures, we can refine the procedures into standards and tool support and automation. And that would be an extremely useful activity as far as these complex issues are concerned. Now, when we face a problem, we have these 4 or 5 issues that I've talked about. And then we have a mechanism to actually address these issues. So wherever we face an issue, we can look at the process from that issue's perspective using the process framework. The process framework enables us to define what is the basic element of a process is, or a task is. And then it also defines the relationship that exists of that basic unit and how it interacts with other elements in the process. Now, this is very important. Once you are able to define that process framework for a given problem, you can then understand where the problem lies. And that's the key in finding solutions to the problems of quality, of product technology, of requirements and stability, and of complexity. And wherever we face these problems, or other problems for that matter, we can use a process framework and define and sort of isolate where the problem is using the process framework. And the basic element of a process framework is a unit cell. That cell is defined to accomplish a specific task and is uniquely identified. Now, for all the different kinds of tasks in a process, we have to define a unit cell. And I'm going to show you a picture of a very simplified picture of a unit cell. Here you have a unit cell which takes inputs and performs the tasks or task, and output is generated. This is the extremely simplified version of a unit cell. What this tells us that we need to decompose our process to such level that we are able to start at the U level and refine that U level to W level and then A level. Then we are able to completely document our process. Now let's look at a detailed description of the unit cell. A unit cell has input, it has an entry section, a task section, and an exit section from where it produces output. And it has in feedback and out feedback. The entry section documents the conditions to be met before task initiation. The exit section documents or shows the results that will be produced. The feedback has two aspects to it. The in feedback is the feedback that we get or a cell gets from other stages, and the out feedback shows the arrow shows the feedback which is given to other stages. The task is what is to be done, by whom, how, and when, including standards, procedures, and responsibilities. And finally, it has measurements. For task, it includes measures of activities, resources, and time. For output, it includes number, size, and quality. And for feedback, if there are any measures, they include number, size, and quality. And so you can see that this is a very detailed description of the basic processing element of a process framework. So if we are able to document our process in such a detailed manner, we will be able to identify and ultimately solve the issues of quality, of product technology, of requirements and stability, and of complexity by understanding what are the entry conditions, what are the exit conditions, what task has to be performed, and what measures have to be recorded, and if there are any feedbacks from other stages, or if this unit provides a feedback to other stages. This is a very detailed description of each task that is included in a process. The entry conditions are those conditions which are necessary for the task initiation, which include inputs from one or more of their sources. It also includes the task standards that will be followed, the procedures that will be followed, if there are any methods and responsibilities, and any required measures are also defined in the entry section of the unit cell. On the other hand, the exit conditions define the results produced, their level of validation, and any post-task conditions that exist when the processing of the unit cell is completed. Now, this sort of documentation allows us to view a cell in terms of contract with other cells, and we can say that if the entry conditions are met and task execution takes place, then we can assure that the exit conditions, the post-task conditions, will also be met. And if that is how our process is executed, and actually if that is how our code is written, then we can get a lot of assurance, and this becomes a mechanism for improving quality of process or of a product, given it is applied in either of them. And the cell feedback refers to any data provided to or received from other stages in the process. So you can see that if we document our process steps or process activities using the process framework approach, we can very easily document each of the steps, first at the highest level, and then as we proceed and refine these universal level processes into W level, and if necessary to A level processes. In order for the software industry to benefit from this sort of approach, IBM developed a modeling language in 1980 and named it as ETVX modeling language, or simply ETVX. The ETVX language is based on the concept of unit cells, and in today's sitting we will be talking about what ETVX language is, and we will use very simple example on actually applying the ETVX language for documenting a process, a U-level process, I must say. The objective of the ETVX language, or ETVX, is to illustrate the effective process performance. As I said, that it can be applied to high-level processes as well as very low-level processes, as low a level as control processes, which are considered very low-level processes in software development. The model of the ETVX is represented in the form of 4 functions which are interrelated. Each of these 4 functions are characteristics of a unit cell, and these 4 functions are, as you can see on the screen, these 4 functions are entry, and hence we have E for that, task, and we have T for that in the language name. Then there is verification, represented by V, and exit, which is represented by X. Now, you must have developed some concept of what ETVX's functions are based on the unit cell discussion that we have had a little bit earlier. But before we go into more details of how this language is applied in documenting or modeling a process, which is very important, let's consider what are these individual functions one by one. What is an entry? The entry section defines the entry criteria that must be satisfied for the process to be initiated and list the work products that must be available as inputs to the process. In other words, we can say that the entry section is where all the preconditions, all the prior work of each of the process step has to be completed, has to be ensured that these prior steps, prior work has been done before a task can start its processing. Let us now talk about the second section, which is the task section. As you can see on the screen, the task section defines the work to be carried in performing the process. So that's, you can say, in other words, is the main thing in the process step. The order of the task is generally, but not strictly, sequential. Some of the tasks may be concurrent with other tasks. You can say that this is where the heart of the process step takes place. The most important activity of the process step takes place in the task section of a unit cell. One of the key things is that the task section assumes that the work done here is dependent on the work or steps that were taken prior to it. In other words, if the entry conditions and the work and steps listed in the entry section have been completed, then and only then can the tasks listed in the task section or activities listed in the task section can be carried out. If the tasks listed or activities listed in the entry section are not fulfilled, then the activities listed in the task section cannot be carried out. It must not start. We must not start the activities in the tasks section of a element of a cell if the prior conditions are not met. Let's talk about the verification. The verification section defines steps for verifying that the process has been properly executed and that the associated work products meet project objectives. तो हम कह सकते हैं कि जो वेरिफिकेशन का सेक्शन है उसमें हम ये इंश्योर करते हैं कि जो इस सेल का मकसद था, इस यूनिट सेल का, यानी जो टास्क्स परफॉर्म होने चाहिए थे, जो एक्टिविटी या स्टेप्स इसमें परफॉर्म होने चाहिए थे, वो परफॉर्म होते हैं, किए गए हैं। और उसको इंश्योर करने के लिए कई मैकेनिज़्म हैं। टिपिकली जो SQA ग्रुप है वो उसके अंदर इन्वॉल्व होता है और वो देखते हैं कि जो स्टेप्स लेने ज़रूरी थे क्या वो लिए गए हैं या नहीं लिए गए। इसी तरह हमने बात की थी कि कुछ मेजर्स जो हैं वो भी कलेक्ट किए जाते हैं और वो भी वेरिफिकेशन की स्टेज के ऊपर ही मेजर्स को हम कलेक्ट करते हैं कि कितना वक्त इस एक्टिविटी को कंप्लीट करने में लगा फॉर एग्ज़ाम्पल, और कितने डिफेक्ट्स थे। अगर फॉर एग्ज़ाम्पल हम डिफेक्ट्स को चेक कर रहे हैं या काउंट कर रहे हैं या डिफेक्ट फाइंडिंग एक्टिविटी है, तो जो भी एक्टिविटी हो उससे रिलेटेड जो मेजर्स हैं उनको भी यहीं पर कलेक्ट किया जाता है। तो इन अदर वर्ड्स ना सिर्फ ये कि वेरिफिकेशन होती है बल्कि एक एक्टिविटी होती है जिसको हम डाटा गैदरिंग कहते हैं, वो भी इसी सेक्शन में होती है, यानी कि वेरिफिकेशन के लेवल के ऊपर। तो अब आप देख रहे हैं कि जैसे जैसे हम एक सेल की डिस्कशन कर रहे हैं वैसे ये बात क्लियर हो रही है कि एक सेल جو ہے وہ بڑی ڈیٹیلڈ طریق کے اوپر اس کو ڈاکومنٹ کیا گیا ہے، تاکہ کوئی چیز ہمارے پاس سے ہماری نظروں سے، پروجیکٹ مینیجر کی نظر سے اجھل نہ ہو، اور ہر چیز کلیئرلی ڈیفائن ہو جائے. جب کلیئرلی ہر چیز ڈیفائن ہو جاتی ہے تو پروسیس کے جو کرٹیکل ایشوز ہیں، جو کوالٹی کے فیئرنیس نہ ہونے کی وجہ سے آ سکتے ہیں، یا پروڈکٹ ٹیکنالوجی کے حوالے سے آ سکتے ہیں، یا ریکوائرمنٹس کی انسٹیبلٹی کی وجہ سے ہو سکتے ہیں، یا کسی بھی کمپلیکسٹی کی وجہ سے ہو سکتے ہیں، تو وہ سارے ایشوز جو ہیں وہ ہائی لائٹ ہو کر سامنے آ جاتے ہیں. اور جب آپ کے پاس ایشوز ہائی لائٹ ہو جاتے ہیں تو آپ ان کو آسانی سے سالو کر سکتے ہیں. میں نے آسانی سے کہا کیونکہ جو چیزیں آپ کے علم میں ہوں ان کا سلوشن ڈھونڈنا آسان ہوتا ہے، سوائے اس کے کہ ہم ایسی ٹیکنالوجی کی بات کریں یا ایسی اتنی کمپلیکسٹی کی بات کریں کہ وہ باقی جو پروجیکٹ کے پیرامیٹرز ہیں، ٹائم اور اسکوپ اور فنڈز، کاسٹ وغیرہ کے لحاظ سے وہ انفیزیبل ہو. یہ علیحدہ بات ہے، لیکن ایٹ لیسٹ وی وڈ نو این آنسر کہ جی کسٹمر آپ کو یہ کہہ رہا ہے کہ 3 مہینے کے اندر ہمیں یہ ایک ایسی ٹیکنالوجی میں ایک ایسی پروڈکٹ ڈیولپ کر دو جو کہ ممکن نہیں ہے. تو اب جب آپ اپنے پروسیس ایک لیٹس سے کہ ETVX لینگویج کو یوز کر کے اس کو کلیئرلی ڈیفائن کر دیں گے تو پھر آپ کسٹمر کے پاس جا کے کہہ سکتے ہیں کہ جی یہ ہم نے آپ کی جو ریکوائرمنٹ ہے اس کو ڈاکومنٹ کیا ہے، اور یہ اس ٹائم فریم کے اندر، اس کاسٹ میں، اس اسکیڈول میں ممکن نہیں ہے. تو ایٹ لیسٹ دیٹس اے سولوشن دیٹ ایگزسٹ. اس کے مقابلے پہ اگر ہمیں پتہ ہی نہ ہو کسی چیز کا کہ پروسیس میں کیا چیزیں ہیں، کیونکہ جو انویزیبلٹی ہے وہ بڑی ایک ڈینجرس چیز ہے سافٹ ویئر پروجیکٹس میں. تو ہڈن چیزیں جو ہوتی ہیں، ہڈن ایشوز جو ہیں، وہ ان کو ہائی لائٹ کرنا، ان کو مینجمنٹ کے علم میں لانا ایک بہت امپورٹنٹ اور ضروری، بلکہ مینڈیٹری ایکٹیویٹی ہے فار سکسیزفل ایگزیکیوشن آف دا سافٹ ویئر پروجیکٹ. تو جب آپ اپنے پروسیس کو اس طرح ڈاکومنٹ کرتے ہیں تو موسٹ آف دا تھنگس کلیئرلی آر آئیڈینٹیفائڈ، اور جو پرابلمز ہیں they sort of jump out of those as a result of that documentation. تو اب ہم آخری جو سیکشن ہے ایگزٹ کا اس کے اوپر بات کرتے ہیں. تو جو آخری سیکشن ہے ایگزٹ کا، یہ سیکشن ڈیفائن کرتا ہے ایگزٹ کرائٹیریا دیٹ مسٹ بی سیٹسفائڈ فار دا پروسیس ٹو بی ٹرمینیٹڈ. جیسا کہ ہماری انٹری کنڈیشنز ہیں، اس طرح یہاں پر ایگزٹ کنڈیشنز جو ہیں وہ ڈاکومنٹڈ ہوتی ہیں. The exact criteria usually defines the completion and verification of work products in terms of qualitative aspects of the products. تو جو exact criteria ہے وہ qualitative aspect سے define کیا جاتا ہے as compared to quantitative aspects. تو جب ہم ایگزٹ کرائٹیریا کو ڈیفائن کرتے ہیں اور ایک پروسیس اس ایگزٹ کرائٹیریا کو میٹ کر کے باہر آ جائے اس یونٹ سیل سے یا اس سنگل ایگزیکیوشن آف پروسیس اسٹیپ سے، تو ہماری جو ایشورنس لیول ہے وہ بہت امپروو کر جاتا ہے، سگنیفیکنٹلی ہائر دین اف وی ہیڈ ناٹ گون تھرو دس ڈیٹیلڈ steps, the sales set of steps using the process framework. کیونکہ جب ہم اس ایکٹیویٹی سے گزرتے ہیں یا اس سیٹ آف ایکٹیویٹیز سے گزرتے ہیں تو ہمیں انٹری کنڈیشنز بھی میٹ کرنی پڑتی ہیں، ہمیں ٹاسک کو فیتھفلی ایکسیکیوٹ کرنا پڑتا ہے، پھر ہمیں یہ ویریفائی کرنا پڑتا ہے کہ یس دا ٹاسک واز ایکچولی ایکسیکیوٹیڈ فیتھفلی، اور اس کے اندر انڈیپینڈنٹ گروپس مثلاً SQA گروپ انوالو ہو جاتا ہے और वो ये वेरीफाई करता है कि यस दिस टास्क वाज faithfully executed, and the necessary steps that were documented using the company's organization standards have been followed. इसी तरह जो हमने डाटा को कलेक्ट करना होता है, जो मेजर्स हमने गैदर करने होते हैं, वो भी वेरिफिकेशन में हम करते हैं. और जब हम ये कर लेते हैं तो फिर हम एग्जिट क्राइटेरिया या एग्जिट सेक्शन से गुजरते हैं और एग्जिट क्राइटेरिया को मीट करते हैं. फिर हम कह सकते हैं कि जी ये प्रोसेस था, इसकी एंटी कंडीशंस ये थी, आपने हमें ये फुलफ़िल करके दी, हमने फेथफुली प्रोसेस को एग्जीक्यूट किया, और हम एश्योर करते हैं कि जो एग्जिट क्राइटेरिया डॉक्यूमेंटेड है एग्जिट सेक्शन में ऑफ द ETVX मॉडल, दैट हैज़ बिन fulfilled, and the rest of the team can get assurance from that. अब उस एक्टिविटी या उस प्रोसेस के बाद में जो प्रोसेस आएगा उसके लिए प्रायर प्रोसेस का जो एग्जिट क्राइटेरिया है वो इनिशियल क्राइटेरिया बन जाएगा या एंट्री कंडीशंस बन जाएंगी. सो इससे जो रिलेशनशिप है between different activities and different processes वो ज़्यादा बेहतर हो जाता है. और जैसा कि मैंने पहले भी कहा था कि एक कॉन्ट्रैक्चुअल बाइंडिंग किसी सूरत बन जाती है. मुख्तलिफ एक्टिविटीज़ के दरमियान द रिलेशनशिप टेक्स द फॉर्म ऑफ कॉन्ट्रैक्ट, एंड सी द नोशन ऑफ द फॉर्मल entry, exit, and that criteria goes with each of them relates well to one of those universal models like the waterfall model that we have mentioned. So if we use ETVX, and it is a very good modeling technique for modeling processes, we take each process step and develop an ETVX model for it. Let's, for example, take the example of inspections. Now there can be a number of inspections, and we can develop an ETVX based model of how an inspection is to be conducted. Or we can develop an ETVX model of test planning, or we can develop an ETVX model of designing software, and so on and so forth. Some of them are at a higher level, like designing is a higher level activity, and it can be further refined into more detailed processes as compared to the one example that I mentioned is developing an ETVX model for conducting an inspection. Now that inspection can be of anything. It can be of a test plan, it can be of code, it can be of software design, but we can have a generic ETVX model for performing inspection, and if we are further interested in developing individual ETVX models for code inspections and design inspections and architectural documents, then we can go one level down further and add more detail to and more specific detail to the ETVX model. And as I had mentioned that you can develop ETVX models for processes at the U level, or processes and standards at the W level, and also at the atomic or A level. So this is a very useful model. Let's talk a little bit about the characteristics of ETVX model. First and foremost, that is a task oriented, as you have seen, and with this, it is very familiar with the U-level models, but it has provisions within it to capture feedback from other stages and to provide feedback to other stages when necessary. One of the other characteristics is that each task must be explicitly defined, and that actually is a very positive and very strong point, a very strong characteristics of the ETVX modeling technique, because you have to think hard to actually explicitly define a task that has to be modeled. And you can develop an ETVX model by both using top-down approach or bottom-up approach. Let's talk about this a little bit. If you are modeling a universal level process, then obviously you have to start at the top, and you have a top-down approach, so to speak. And using that approach, you can actually refine your U model into W models, and if necessary, into A-level models. But on the other hand, you can also use the A-level models, collect them using the bottom-up approach to compose them into a W-level process. For that, you have to start at the most detailed A-level processes, define different activities, and then compose them to make it at the, or convert it into a W-level process. And many software design development approaches encourage bottom-up development. So software engineers are trained in both top-down as well as in bottom-up modeling techniques. They know how to decompose using the top-down approach, or use and do composing or composability approach to using the bottom-up technique to convert the A-level or atomic level processes into W-level processes, which are at the higher level than A-level, and then eventually into the U-level processes. So this is a very strong characteristic, a very valuable characteristic of the ETVX model. Let us now take an example of the ETVX model, and we will start off with the generic activities of different process models at the U-level, the universal level, and we will talk about, if you take, for example, software development process, there are 3 activities which are included in all process models, and they are design, implementation, and test. And these activities at the highest level tell you that some design activity will be done. How that will be done is not clear. When you say implementation, typically this means that programs will be developed, but does not tell you the order, does not tell you the other related activities, like would the unit test be done at the implementation level or not. And finally, when you say we are in the test process or performing test activities, it does not tell you whether it includes unit tests or it's just system and integration tests. And so, but all of these 3 are major parts of any software process model, and all of them are included in U-level process models. Now, when all of these and any of these activities are further decomposed, or as we say, broken down into more detail, significant differences show up if you are using waterfall model, or if you're using spiral model, or if you're using one of the iterative development approaches, or if you're using one of the rapid development approaches. So the detail where the differences actually appear on what is design, and how much do we design, and what are the prerequisites of design, and what are the entry conditions and post task conditions for each of these activities. And so when we are at the W level, for example, where the differences start to appear, many activities can still be relatively standardized across different projects. Even though there are many variations, there are still many activities which can be standardized. And so with that, we can establish some basic processes that can be interconnected in different ways to meet unique project-specific requirements or needs. And if we are able to document our processes that way, then we can certainly improve our execution of the process, because with every project we have to have certain activities which are kernel or required or mandatory. On the other hand, there are certain activities which are optional and are not required or not needed in some projects, while in others they are needed and must be performed. And still further, we can go one level down and decompose the W level activities into A level activities, and still the same concept of standardization and individualistic needs would be applicable at the A level processes also. So let's now look at the design, implementation, and test activities in all process models. They are defined as defined at the U level using the ETVX model. Here you can see an extremely simplified version of design, implementation, and test. As you can see, the requirements become the input to design, which produce a design document which are fed into the implementation task as input. The implementation task produces the code, so to speak, and the code is taken as input into the test task, and after the performance or performing of the test task, the software is released, or software is becomes the output of this process. We can also see that requirements issues are fed back to the requirements activity or requirements task from the design task, from the implementation task, implementation cell, and from the test cell. And implementation issues are fed back to the implementation cell by the test cell, and design issues are fed back to the design cell from the implementation cell. And the picture is fairly clear and straightforward, and it really does not require much elaboration. You can understand it very quickly that this is actually how things are modeled in all the software process models, whether it's a waterfall model or it's a spiral model, but at the highest level. This model, however, does not tell you anything that goes inside of these individual cells that we have seen. Now, if we develop an ETVX model of this description, what did it look like? For the ETVX model, we need to have, and for each cell, we need to have an entry section. We need to have an exit section. We need to have feedback in, feedback out, the task, and the verification. Now let's take, for example, the design cell. What do you think are the entry conditions for a design cell? The entry conditions, obviously, for a design cell are approved requirements and changes and development plan. So anything that has to be finished before the design starts has to be finished before the design starts. Now, what can be the entry requirements or entry conditions for the implementation cell? Obviously, that's an inspected and approved design and any changes that come along. So we see that you cannot start implementation, or you cannot go through an iteration of the implementation cell unless you have an approved design. And we approve the design by performing the inspection on the design document. And finally, let's consider the entry condition for the test cell, and that has to be the inspected and approved code and any changes that are sent afterwards. So you see that for each different cell, we have a set of entry conditions. And when we talk about the exit conditions for the design, it has to be the inspected and approved design and any changes afterwards. The exit condition for the implementation cell is inspected and approved code in the first execution of this of the implementation cell, and if there are any changes that have to be approved also. And for the test cell, the exit condition is inspected, tested, and approved software. So you see, if we can associate with each cell the entry conditions, the exit conditions, and we ensure that the entry condition, and we are assured that entry conditions are met, the task is performed accurately, then we can ensure other cells or other participants of the process that what you're getting is an assurance on what we have listed as the exit conditions for a particular cell or a particular process step. And for feedback, we have the design issues and implementation issues that go with each cell. Now let's talk a little bit about the task related activities. For the design cell, the task is obviously to perform the design activity. For the implementation cell, the activity or task is implementation, that is coding, inspection, and unit test. For the testing cell or for the test cell, the testing has to be done from integration perspective, from function testing, system testing, and acceptance testing, obviously depending on what kind of tests are documented and agreed upon between the client and developer. So in today's lecture, today's sitting, we had discussed the need for a process architecture to address the problems of quality, problems of project technology, of requirements, instability, and of complexity. And we have learned a language. We started to learn a language to model process steps. That language is ETVX. That's about it. Thank you very much.